Hello, and welcome back to problem number 2. Add two numbers in LeetCode. I think we're just going to get stuck straight in, so let's read the question. You are given two non-empty linked lists representing two non-negative integers. The digits are stored in reverse order, and each of their nodes contains a single digit. Add the two numbers and return the sum as a linked list. You may assume the two numbers do not contain any leading zero except the number 0 itself. Okay, so it sounds like, and according to the example, when we have a linked list like 2, 4, and 3, really what we're saying is this is 342, right? Our linked list is representing a number and is being represented in reverse order. So that means this is 342. 5, 6, 4, 6, 4 is 465. All we have to do now is add these two numbers together. So what's 465 plus 342? Well, it's 7, 0, carry R1, and 8, 807, right? And then we'd have to return this as a linked list in reverse order again. So it'd be 7, 0, and 8. Is that right? It is. Okay. Seems like a pretty straightforward problem. How might we solve this? What if we could step through both linked lists and add the numbers together and simply return add them into a new node in a new linked list and then return our linked list at the end. Well, let's try and do that. Well, um, let's take the next example with all those nines, or example 3. 9, I think there's 7 of them. 2, 3, 4, 5, 6, 7. This is our first linked list, and then our second linked list looks like it has 4 nines in it. Okay, so let's imagine we're creating a new node every time we step through these linked lists together. What would that look like? So we'd say, okay, 9, grab a new color here. We'd say 9 plus 9, oh, that's a plus, is 18. However, we can't just add this into a new node because it looks like each of their nodes contains a single digit, right? And that's an important rule for this problem, but also it makes perfect sense, right? Your answer wouldn't be correct. What you really need to be doing, just like in basic addition, is you need to be carrying this 1. So what would this actually look like? Well, we need to say the new node contains 8, and we could get 8 by just saying whatever this number is, modulus 10. So modulus 10, which will always give us essentially the remainder after we get rid of the 10, right? If we had 18, then 18 modulus 10 would be 8. So we'd put 8 in the node, and when we know we have this remainder, this carryover, I should say, we know that we need to have our carry in the next addition that we do in the next node. So let's go to the next node. We'll say 9 plus 9 is 18, but this time we have a 1 to carry, so that'll be 19. And just like before, we'd say it's 9, and we'd carry our 1, and we'd keep going on. So 9 plus 9 is 18, plus 1 is 19. So we'd say again 9, carry our 1, 9 plus 9 is 18, plus 1 is 19, so 9, carry our 1, and this time we just do 1 plus 9, which is 10, so this time would be 0, carry our 1. Again, same thing, 0, carry our 1, 0, carry our 1, and this time all we have left is our carry. So this would be our answer, 89990001, each of those numbers being a number in our a node in our linked list. So how do we determine our space and time complexity? Let's start with time complexity. So what are we really doing in our example here? We're stepping through each node once at a time in our linked list until we have our solution. So really the problem scales depending on the length of the longest node because we have to always go through the longest node. So if, for example, we have 4 here, we would step through 4 times. But this one's a lot longer, so we would have to at least step through 7 times. So the way our time complexity scales is depending on the length of the longest linked list. So we would say something like O is max, meaning essentially which is the longest, between our first linked list, let's call it M, and our second linked list, let's call it N. And that would be our time complexity. Our space complexity is very similar. The number that we're storing is essentially going to be the length of the longest list, potentially plus 1 if we have a carry at the end of it. So really, our space complexity is exactly the same. Max m n. Okay, let's try and code this up. So first of all, we know that we need to return a linked list. So let's create a linked list. We have this definition of what the nodes look like up here, which is given to us by LeetCode. So let's create a linked list. Let's say let's get the first uh, let's get the first node. So we'll say struct list node malloc size of one of the nodes. Okay, so that will give us the head of our linked list. The way that we're probably going to want to create the linked list as we go along is to have this kind of fake head. This is going to be the first node in our linked list, but it's actually going to point to the beginning of our linked list that we want to return. This is just helpful for creating a linked list the way we're going to do it. So we want a pointer to really point to that is going to kind of so we want a pointer that is kind of going to be pointing to the head for now, but is going to be stepping over the linked list and helping us add our new nodes as we go along. So let's make it just a pointer, which is going to point to the head for now. We'll call it current, and we'll point that to the head. And now we need to probably have a variable to store our value for when we add two nodes together. And we also talked about the concept of our carry. So for now, our carry is going to be 0. And okay, so we have our two linked lists. How do we step through them? Well, we're going to keep stepping through both of them together until we reach the end of the linked lists. So we want to say, while our first linked list, L1, is not equal to null, aka we haven't reached the end, or L2 is not equal to null, is not equal to null. So now we're stepping through both linked lists, but if we try to do this, we might run into the problem of if the linked lists are of different lengths, we might start trying to do something in a linked list when really we're not allowed to. We've reached the end. We're trying to access a node that doesn't really exist, and that's going to give us errors. So we need to make sure that we're handling the case where each linked lists are of different lengths. So we need to check again if L1 is not equal to null. So if just L1 isn't equal to null, we need to say, okay, if L2 we also haven't reached the end of, then we know in this case, in this specific case for sure, we still have both nodes to add together. Okay, so if we know we have both nodes to add together, our value is going to be equal to L1 val plus L2 val. And we need to remember to add our carry, which for now is 0. We don't have any carry yet, but we have a carry. And now that we've used these two nodes, we can step over to the next node. So let's say L1 is equal to L1 next. So now we're pointing at the next node, and we'll do the same for L2. L2 next. Okay, so we've handled the case where we know we still have both nodes, but what if out of both linked lists, only the first linked list still has a node and the second, and we've reached the end of our second linked list? Well, we would say else. This means that we don't have anything to do in our second linked list anymore. So we could say only L1 exists for us to work on. We'd say val is now equal to L1 val, and we don't add it to L2 obviously, but we just add our carry. And again, we move our pointer along. L1 is equal to L1 next. So now L1's moved up. So in this case, our first linked list still had nodes, but if it doesn't, then we reach the point where we only have nodes left in our second linked list. So we kind of do what we did with the case where we only had L1, but obviously for L2. So L2 val plus carry, and then we move our pointer along to point to the next node in the list is equal to next. Okay, so we've almost done. Really what we're doing is so far we're just finding the value and we're moving up. We're finding the value and we're moving up our pointers in our linked list. We're moving along in these nodes. what we need to do really is actually create our new linked list, which contains all of our values. So what we want to do is we want to say, let's start creating new nodes for our answers. I want to say linked list node times new. So every time we go through this loop, we're going to be creating a new node. Struct list node malloc size of list node. And we want to say the new value isn't just value, but is value modulus 10, because remember we may have a number that's greater than 10 in here, and all we want is the remainder after we do modulus 10. And new next is going to be equal to null, because this is going to be the most recent node we have. So now what we want to say is the pointer that we created earlier, which kind of points to our fake head, current, we want to say current next is going to be equal to this new node that we created. And then we want to say current is also equal to new. So all we've essentially done is we've added our new to the end of our linked list. And then we've also moved current up to point at that new. So we know that when we loop through this again, we can again add our new node at the next current. Now we want to make sure that we actually set our new carry value. And we're going to have to do value divided by 10. Essentially what this does is imagine you have something like 18 in integer division. When you divide this by 10, it will give us an answer of 1, and it will scrap or get rid of the remainder. So instead of 1.8, this is just going to be 1. So that's always going to give us a carry if we actually have it. Okay. Oh, carry. Let's not delete that. Carry is equal to val divided by 10. Okay. So this is going to create a new node in our new linked list, which has our answer in it for every single case. However, we need to also make sure that if we have a carry at the very end, that we include that carry in our linked list. So in the previous example, we had that one carry on its own, but we need to make sure that we have a node for that as well. Let's not forget about that. So we'll say if carry, we want to make another node for that carry. So let's copy this across over here. Struct list node, and then we want to say new val is equal to carry, or we could just say 1. New next is equal to null, because it's going to be the tail, the last node, and current next is equal to new. Okay, finally, what we want to do is return our linked list. And don't forget, we created this kind of head node at the beginning, which we're not actually using. This is just kind of to help us start our linked list. Really, it starts at head next. So let's say current is equal to head next, and then we would return current. And seeing as we're not using this node that we created at head, we should really, to avoid memory leaks, free that memory up. So we should say now free head. We don't need that memory anymore. Okay, I just noticed there was a small bug in the program. I should have had struct list node in here. I didn't have the capital letter or the struct, and I copied it over, so the problem is here too, but that should hopefully be it. Okay, cool. So we completed our problem.